Okay, so welcome back to PChem Crash Course. So in this PChem Crash Course, I want to talk about the contributions to energy of ideal gas molecules. So to start that, let's consider that we have essentially a container of ideal gas molecules. And actually, let's say ideal gas atoms. This container is going to comprise gas phase helium, ideal gas. So I can draw that. I have some container. Oops, that was horribly drawn. So take this. This is a container. In here I have helium atoms. These helium atoms are not stationary. They're moving all around. Maybe. And I am not the best at drawing, as we know. So I'm just, trying to do my best here. So there's helium atoms in this container. So one question we might ask ourselves, what is the energy of this sample? So we got these helium atoms. If I was going to probe the energy of this thing, what would it be? And that's maybe a confusing question if you are a chemical engineer, because typically when we think of the energy of a sample of something, you have to tell me what the reference state is, right? So what do you mean, what's the energy? Are you talking about the energy of just helium? Because, I know I can go look the heat of formation of that, of helium up, and I know that it's going to be 0 because helium's in its, standard state here. So what do you mean the energy, right? Helium doesn't want to react with anything. So I don't, am I talking about the formation of helium from some other compound? That doesn't make sense. So a simpler question might be, what is the energy of a single one of those helium atoms? However, that question may still be tough to answer. We're going to get there throughout this lecture, but it at least gives us a starting point. We can begin to answer that question by thinking about the contributions to the energy of a helium atom. I don't know why my OneNote jumps around like that. Okay, so the helium atoms, so to think about the contributions, let's think about these helium atoms. So the helium atoms, and a sample that we drew above, we said they are ideal gas atoms. By ideal gas, what we mean that the helium atoms don't interact with anything. So maybe that's, let's say, I should have kept that one. So let's say they don't experience interatomic interactions. So what I mean by that is that in the perspective of any given helium atom, it is completely isolated, completely alone in the world. Nothing else exists. It doesn't interact with anything. It doesn't experience van der Waals interactions. It doesn't experience any sort of chemical bonding or non-bonding interactions. To all it knows, it is alone in the entire universe. The only thing that exists is it. So we don't have to worry about potential fields from other atoms or molecules because they don't exist. So no Okay, so the only other contributions to the energy of the helium atom are going to be the electronic energy. This is what we saw in PChem Crash Course 1. This is going to be the kinetic energy of the electrons within the helium atom pursuant to the field that is set up by the nucleus, so the 2 protons within the nucleus, and then also the interactions of the electrons with each other. And to be honest, that is more complicated than I want to get into, but that's just the contributions that are there for that electronic energy for that helium atom. The other is going to be the translational energy. So we drew this thing, all these things are zipping around in there. They've got translational energy as well. So we saw in PChem Crash Course 1 that the electronic energy comes from the Schrodinger equation, where the psi are going to be the atomic orbitals and the energies are going to be the energies associated with those orbitals. For the helium atom, we have 2 particles in there. We have meaning we have 2 electrons, so we basically solve for the wave function and energies of both of them. What we get is that both energies occupy the 1s orbital. One electron is going to have a spin up and the other one's going to be a spin down. So for any given helium atom, the energy will be that associated with a 1s2 orbital. What we mean there is that the electrons one spin up, one spin down. They have energies associated with that circumstance. And I can tell you that, and that probably makes sense, to get to the math on that, to jump from the math from hydrogen to helium. There is so much of it. This is why I want to ignore that. Okay. So within this sample of helium, there could be a distribution of energies depending on the fraction of helium atoms that are in excited states. However, this is going to be very low. The fraction that is in excited state is going to be really low. It's not impossible. There's nothing is impossible in quantum mechanics. But it's so low that when we observe the sample of helium atoms, we're going to be observing essentially this ground state energy. So we're going to say, for our purposes, where we are looking at this sample of helium atoms, so we're looking at this sample of helium atoms, yes, these are quantum particles, but we're observing them from the classical world, right? So we're not, we are going to observe the average energy of these things, and that is going to be almost identically in our world. For our purposes, it's going to be almost identically to the energy of ground state helium. Okay. So that's the electronic piece. What about the translational piece? Okay, so this is where we're going to need to perform some modeling and do some calculations. So yes, these are helium atoms, and we are observing them from the classical world, but we cannot know their translational energies without quantum mechanics because they are quantum particles. So we got to do a little bit of quantum. I will show in the next lecture that we're going to start the analysis of something like helium out in a quantum way, but we're eventually going to acknowledge that helium at temperatures above really, really cold is going to be a classical particle. But we're going to deal with that later. We can't start out the model as a classical particle. We can only simplify the model later to model it like a classical particle. But at first we got to start out with a quantum model because it's a helium atom, right? How is it moving, right? It's moving pursuant to some potential. I'll show that in just a second. And the only way to describe those motions and the translational energies associated with them is to treat it quantum mechanically. So we need a model to do that. Treating it quantum mechanically, we're going to use H psi equals E psi. This time, so in the last example, we talked about using H psi, E psi, where the particles were the electrons within the atom. Here, we're going to use H psi, E psi to describe the atoms themselves. So just like we can calculate the potential energy of, if I hold my pencil like this, we could calculate the potential energy of the pencil itself, or we could calculate the potential energy of maybe just the tip of the pencil, right? We can do the same thing using the Schrodinger equation on the helium atom. We can use it to describe the electrons within the helium or the helium atom itself. We can define the particle in whatever way we need. Okay, so to do this, we use a model called particle in the box. This is a model to describe a non-interacting particle whose only constraints are I'll say the walls of a container. So if I want to draw this thing, I'm going to draw maybe a two-dimensional box. And I'm just going to draw a single particle in that box. What I'm going to say here is that the potential so this is going to be, maybe I should specify this a little bit better. My potential is going to be this potential energy operator. So what is the potential that's felt by this particle, in this case our helium atom? Inside the box equals 0, non-interacting. Like we said, there's lots of helium atoms in this box, right? So this is our actual box. There's lots of helium atoms in it, but they don't see each other, right? They're ideal gas molecules. The definition of ideal gas is non-interacting. To these helium atoms, they are the only thing that exist in the universe. However, their universe is very small because it's just the box. But this is how we're going to model it, right? This is the exact picture of that. So inside the box, there's no potential because there's nothing to interact with. Potential at the walls equals positive infinity. What this means is, and this is just a model, this is the way we're stating this. By stating this, what we are stating is that the particle can't tunnel through the wall, right? So it can't get through the wall, right? It can't leave the box. It's trapped in the box forever. It can't get out. So, I mean, forever is maybe confusing. I mean, it's the model that we are not modeling whenever this particle gets out of the box. We are only modeling the circumstance when it's in, and the only way to constrain it in a box physically and mathematically is to say that there is an infinite potential energy associated with escaping that box. So basically, this molecule hits the side of the wall and it bounces off, right? So it does not tunnel through. So that works, that does not. That's what I mean by that. Quantum particles indeed can tunnel. We are not going to deal with that. That's a complete distraction from where we are going. Okay, so I am not going to solve this model. Actually, I think solving this model is pretty fun, but I'm not going to do it because it requires too much explanations of math. I will tell you that the energy levels, and also the wave functions, so the wave functions and the energy levels for this solution are very well known. People have solved them repeatedly, and we can look them up. I'm not going to solve them here because of that, and I'm not going to talk about the wave functions because we're talking right now about energies, and I don't even really know that that it's useful here to go into all of the information that the wave function gives us. It is very interesting. If you're interested in that sort of thing, I recommend taking a look, but we are interested in energies because that's where we're headed. How can we use this information to construct energies for molecular level chemical reactions? So I'm not going to talk about wave functions. I'm just going to talk about energies. Okay, so we know what the energy levels are. They look like this. In this equation, H is Planck's constant. You can look that up. M is the mass, the particle, which here is the helium atom. A, we've actually done here, I've consider, I've drawn a two-dimensional box. Drawn a two-dimensional box, but in reality it's a three-dimensional box and it's a cube. A is the length of that. The n's and x and y and z are quantum numbers in x, y, z directions. So each helium atom is going to have a translational energy and wave function in all three directions, x, y, and z, and then it's going to have a quantum number associated with that. The quantum numbers for the translational energy levels, that basically tells you I have, my energy levels are discretized, which one am I in. They can span, these span, I don't remember, I think these span from 1, yeah, they span from 1 to positive infinity, so there's infinitely many energy levels, but they are discrete. They can only be integers. They are discrete quantities. Again, I don't know if I'm using the right version of discrete here, but I mean the discretized, quantized version of it. Yeah, so these are analogous, so we know probably quantum numbers that are more familiar to us as chemical engineers are those associated with the orbitals in an atom. So we think about orbitals in an atom, there's 1s, 2s, 2p, 3s, etc. The number on the beginning of that is the quantum number. So 1s, quantum number is 1, 2s and 2p, it's 2, etc. In the particle box, this is what's an analogous thing here. We're just saying which translational energy state are we in, and we can have various values that span from 1 to positive infinity. Okay, so for any given helium atom, if we could pick a helium atom and we knew what its quantum numbers were, we could determine its translational energy using this formula. Unfortunately, we cannot know that because we can't measure the quantum states of a quantum particle, because in doing that we have to shine light on it, which adds energy and changes its state. So we can't know that, but if we did, we would know its energy. I'm going to leave you with that for now. I know that's frustrating, but I'm going to leave you with that for now. I'll show how we can obtain the energy of the sample in the next crash course lecture. Let me leave you with 3 things about that. One, most molecules are in excited translational states at ordinary temperatures. So in ordinary temperatures are quote unquote hot enough that most particles are going to be in an excited state. We can't know the energy levels of any one helium atom because we can't measure them without disturbing the atom, so we can't know what the distribution of, we can know that, and I'm going to show that in the next lecture, but we can't know specifically for any one atom what state it's in. And in reality, that's okay, because we're actually interested in the average translational of the entire box of helium, and I'll show how to do that in the next crash course. Okay, so now we know the energy of a single helium atom within the sample. Well, kind of. We don't know its quantum numbers, but I'm going to leave that open. We're going to get there. What is the energy of the sample? That's going to be, if I take number of atoms in the sample times their energies, and in fact, let me write that differently. If I take the sum over atoms and I sum up their energies, I'll get the total energy. This is something I'm going to address in the next lecture. Okay, So that's helium, which is an atom. What if I have a molecule? Again, we'll say ideal gas, where each molecule contains multiple nuclei. So let's consider a simple case of that. I have a diatomic heteronuclear molecule. How do I change that? So how do the contributions to the energy change? Now, additionally, have vibrational and rotational to the energy. So vibrational means I have my two nuclei, and basically I shouldn't draw it that way. I'm getting ahead of myself. So I have these two. So this is the carbon monoxide molecule, very poorly drawn. But basically what happens is that the nuclei vibrate against each other, so that gives energy. And then rotational means I've got this, and not only am I whizzing through space, but I'm tumbling. So I'm tumbling through space. So I have translational, I have vibrational, and I have rotational. And that's going to be in addition to electronic. So again, the carbon monoxide molecule is a quantum particle. Some of these energies we're going to be able to describe classically. We're going to get to that in the next lecture. Some of them we can't describe classically. So we're going to start out, since this is a quantum particle, we're going to start out using H psi, E psi to establish the energies. We're going to hence need to fill in our Hamiltonian, our kinetic and potential energy, and we're going to do this using models, just like we did for the translational energy. The models are not perfectly accurate. I'll show you why. I'll give an example why. But they are mathematically efficient, and they provide reasonable results for most systems. Okay, so to model the vibrational energy, we use the harmonic oscillator approximation. What that says is that I'm going to put the two nuclei, I'm going to attach them by a spring, and the spring is going to vibrate based on the potential that's set up between those two nuclei, and also pursuant to a spring constant. The harmonic oscillator energy levels. So let me start out. The energy of, if I took, this is going to be, I don't want to write it that way. So if I take here and I say this is carbon and oxygen and I have a distance between them, I could say that the energy, that's kind of poorly drawn. Let me fix that quick. Well, I'm not going to. This should be going to 0 more soon, but there we go. That should not go above 0. That's flat out. Okay. That's going to be actual. Harmonic oscillator goes kind of like this. I'm drawing this horribly. So the nice thing about harmonic oscillator is it captures, the most likely region well. It doesn't capture this region well, and it doesn't capture this region well. But in normal vibrations of a molecule, you're not getting that far out. So as long as you don't heat the thing up such that it's vibrating really violently, you're basically going to be in about this range. So a normal harmonic oscillator that's subject to ordinary temperatures is going to remain maybe in that range, and so the harmonic oscillator model works. Let's see here. So again, for the harmonic oscillator, this is a very well-known model. The wave functions are well known. I'm not going to talk about those here because they're interesting, but it's a distraction from where we're going. I'm going to talk about the energy levels. Those are also well known, so multiple people have solved this model. We don't need to. They look like this. Why it keeps jumping around. Okay. Here, H again is Planck's constant. There's two symbols that look alike here. One is V. That's V. This is the, wait, this, sorry, I get that wrong. This is the Greek letter nu. This is V, like the letter in our alphabet. So nu is the vibrational frequency of the molecule. So this for carbon monoxide molecule is well known. This has been measured many times. It's been calculated many times. We could go look that value up. Basically, it's the frequency of oscillation or vibration of the oxygen against the carbon. V is the vibrational quantum number. They can span from 1 to positive infinity. Must be integers. Hence, for any given carbon monoxide molecule, if we knew which vibrational state it was in, we would know its vibrational energy. Like for the electronic energy, most molecules are going to be in their ground vibrational state. However, it's not as dramatic as electronic energy. For electronic energy, like almost everything, it doesn't matter how hot you are. You could be at 1,000 Kelvin and almost all of those molecules or atoms are going to be in their ground state. Vibrational energy, most things are in their ground state, but there's a population of things that are in excited states. But it's not like translational where most things are in their excited state. Okay, so that's vibrational energies. If we wanted to know the vibrational energy of the sample, we could sum over everything. We would have to know what all the states were, though, and like I said, I'll get to that in a second, or I'll get to that in the next lecture. To model rotation energy, we use what's called the rigid rotor model. A picture of that is here. Basically what it shows, we've got two masses. So mass 1, mass 2, maybe that's carbon and oxygen. And they are connected rigidly. So we know that they vibrate against each other. We just saw that, but in rigid rotor they are rigid. So maybe my carbon is here and my oxygen is here. This pencil is not flexible. So now we're not talking about the vibrational aspects. We're talking about the fact that this thing can tumble around. And how does it do that? Based on the moment of inertia that is set up by these two masses. Again, I'm not going to solve this. I'm not going to talk about the wave functions. I'm only going to talk about the energy levels. For a diatomic heteronuclear molecule, these are well known. They are here. Here, h bar is Planck constant divided by 2 pi. J is the rotational number. I is the moment of inertia of the molecule. Which we know, the moment of inertia depends on the distance between these two masses, the distance between the two nuclei, as well as the masses of the nuclei. For CO, we know that. So we know the moment of inertia. Hence, if we knew the rotational quantum number, like which rotational energy state is it in, we would know the rotational energy of the CO molecule. And if we knew that for every CO molecule, we would know the rotational energy of the sample. Like for the translational entropy, like the translational energy, most molecules are in excited rotational states at ordinary temperatures. So ordinary temperatures are hot on by molecular standards. Hence, they translate and rotate in largely excited energy states. Like for the vibrational energy, molecules with more than 2 atoms. And vibrational, it's if I have more than 2 atoms, then I have multiple vibrational modes that I need to account for. When I'm talking about rotational states, it's atoms that are molecules with nonlinear shapes are going to have multiple moments of inertia that I would need to account for. I'm not going to get into all that because I just want to use these things to illustrate, but you see how this can become more complicated the more complex the system gets. We'd have to account for all that. Here, I think it's, what I want to basically do is illustrate these contributions to energy, where the energies of these particles come from. They come from quantum mechanics because they are quantum particles. Leave it at the fact that because these atoms and molecules are quantum particles, they don't have continuous energies. That means that to know their energies, we would need to know their quantum states. I can't know the quantum numbers or quantum state for any quantum particle because I can't measure it, because if I did measure it, I'd disturb it and then I'd get a different answer than it was originally. So essentially I'm changing the energy of the sample. And that's going to lead me to my next lecture where we're going to say I can estimate the energy, the distribution, which allows me to find the average energy of any sample as long as I know these energy levels that I got to here as well as the temperature of the system. And I'll show that in the next lecture.